we have learned that force analysis of some moving mechanisms can also be solved by using statics principle that we have used in engineering mechanics. In this video, we are going to solve a static force analysis problem of a slider crank mechanism, which will be solved by a graphical method. Okay, let's get started. Hello, I'm Dr. V. Jayakumar. Welcome to my channel. I'm making lecture videos for the benefit of mechanical engineering students. If this is your first time and not yet subscribed yet, please press the subscribe button and also the bell icon so that to get notified all my upcoming videos. Let us get on with the problem. This is the given data. Let us read the problem carefully. For the slider crank mechanism position shown below, an external load of F equal to 3000 Newton acts horizontally on slider 4. The linkage dimensions are given. AB, BC and BAC are given. So we need to determine various forces acting on the links. So given data are mechanism dimensions and applied force at slider F. We need to determine the various forces acting on links and also the driving torque. Here, very important thing is they have mentioned that the mechanism in static equilibrium. That is the key there. Before getting on with the solution, we have to understand how come a slider crank mechanism will come under static force analysis. Considering the mass of the piston and connecting rod, it has significant acceleration. In that case, it cannot be a static force analysis problem. But in this case, we assume, it's a very crude assumption though, we assume that mass of the various links, including slider and connecting rods, are negligible, and also the acceleration is lower, and hence m into a, the inertia forces of the moving components are comparatively lower when compared to the applied force, in this case 3000 Newton. The second assumption being, we do not consider the frictional forces between piston and the cylinder and so on. This assumption makes this problem suitable for static force analysis problem. What is the logic involved? What is the concept involved? Concept is so simple. When a mechanism is in static equilibrium, we can say that each and every link of the mechanism will be in equilibrium. So when I say slider crank mechanism is in static equilibrium, then it is very important that all four links of the slider crank mechanism also should be in equilibrium. This logic gives us that it is a statics problem. I can draw free body diagram for all the four links, and I can attack the problem the same way as we did it in engineering mechanics. Is that clear? This is the concept used. Right. What is the procedure to be used? The same procedure that we have used for 4-bar mechanism, which you might have seen in my previous video. What is the notation we will use? We will use force F suffix ij. For example, here when I say F34, the force exerted by link 3 on link 4. This is the force notation we are going to apply while solving this problem. So what is the step number 1? This is the typical mechanism given. We are going to redraw the diagram geometrically using some suitable scale. So I take the scale 1 centimeter equal to 50 millimeter for a length. Then for a force, I am taking 1 centimeter equal to 500 Newton, right? Based on the given dimensions. Let me draw the axis line. Arbitrarily, let me start somewhere here. Angle is 60 degree given. So I have taken the scale, the length is 100 mm. So as per my scale, I should be drawing 2 centimeter line. Now I need to go for length of the connecting rod. So it is 300 mm, therefore scale is 50 mm. So I need to draw 6 centimeter line. Is that clear? So now let me join this connecting point to mean that this first link is fixed. Now we will give the naming of the links. The fixed link, we call it as 1. So we can call the crank as 2, connecting rod as link 3, this slider as 4. Now we have to represent the force. Yes, we have obtained configuration diagram at the end of the step number 1. Now we will move on to step number 2. Step number 2, you know that we need to draw free body diagram of all the links. But as we are aware, the link 1 is a fixed link and hence it will not have any free body diagram. So we have to draw free body diagram of the remaining 3 links now. How to draw that? We have to draw a parallel line from the configuration diagram. But here what I could do it is I could copy each and every link. So here I am going to draw a parallel line just by dragging them here. This is link 2. If wherever I drag, this will be a parallel line. But when you do, please remember you should be drawing the parallel line. Either using the roller scale or set square or use mini drafter as you wish. Now we will be showing various forces acting on those links, for which we must be aware of the applied and constrained forces concepts. If you take link 2, what are the forces acting there? Of course, there will be some force from 1 to 2. In this 3, the force will be acting on opposite direction, right, along the link. This is what we call constrained forces. Constrained forces always will act in pairs. Similarly, here I will have one pair of constrained forces. Okay, of course, this link 2 will be additionally having the torque. I don't know the magnitude right now. I don't know the direction either. Let us see the force. So here there will be a constrained force. So this is the direction of the force. We call the name of the force as, this is force given by link 3 on link 2. So what is the name? How can we designate? This is F32. What will be the direction of force F12? Might look like we do not know it, but by applying the logic that when the crank will rotate, only when we will have F12 in such a way that F12 and F32 form a couple, which will result into a turning moment of a crank. So using that logic, the direction of F12. So link 3, as you could see, it's a 2 force member. So I will be having a constrained force here. So I will be drawing here one constrained force parallel to link 3. Similarly, at this end, I will draw a constrained force. So what is this name? So this is here. This is acting here, right? This is force exerted by link 2 on 3. This side, we have link 4 exerts force on link 3. So we could say link 3, that means connecting rod link is a 2 force member. Shall we move on to the last one? Slider. What are the forces? Yes, we have applied force 3000 Newton. Then link 1 will exert force on link 4, isn't it? Link 1 is nothing but a fixed link. So fixed link will exert some force on the slider. So what is it notation? F14. What is the direction of the F14? Since it's fixed, when it slides, obviously it will be acting normal to the slider. then you must be asking F14 can be even downward also, because from the other end, you are right. So even this can have this side also, but I know that it is a vertical, but whether moving upward or moving downward, the reaction force or F1 force, we are not sure right now. Is that clear? It can be in any of the directions. I agree with you. Now, is there any other force? Yes, we have some force here acting here, isn't it? We have considered constraint force this direction. Now it always acts in pair, so we need to consider the other partner which will be exerted by 3 to 4. So this one we need to consider. So how can I do? We have to, of course, draw a parallel line. What is the name? This is F34. Yes, we have drawn free body diagram of all the three links now. Yes, we'll move on to step number 3 now. In step number 3, we have to apply equations of equilibrium that we have studied before to each and every link to find the unknown forces. Right. Let us see where to start. Can we start from link 2? Do we know F32 magnitude? No. F12 magnitude? No. I know that it is equal to F32 and hence F12 also I don't know. Do we know T? No. So we have three unknowns. So we cannot try to find the answer now. Move on to next one. Do we know F23 and F43? As of now, no. So we can't start from there also, right? So from where we can start? We can start from here. Why? We know the direction of all three forces. So three force member can be in equilibrium only when those three forces acting on the link should form a force polygon, closed force polygon. You know that there are two conditions of static equilibrium. Summation of F is equal to 0, summation of M is equal to 0. So here by applying the summation of F is equal to 0, when we have three forces are acting on it, when we draw a force polygon, the force polygon must be a closed force polygon. Then we can say the three force member is in equilibrium. That means these three forces must form a closed polygon. That is the clue. So I am going to draw a force polygon now. This is applied or external force, given external force F. So I have used this data. So I do not know the magnitude of the two remaining forces. So but I know the direction. From end A, I have to draw the next vector. It's a vector addition. So I can take F34 or F14. Let me take F14. Do I know the direction? Yes. Magnitude? No. So simply I draw a line to some approximate length. So I start from here and I draw. I don't know whether upward or downward. Right now I am assuming that way. Next, only when I know the exact length, from there I can draw the third vector. But in this case, I do not know the exact length, magnitude of the force. So how can I proceed? But I know that these three forces are going to make a closed polygon. So what can I do? I can start from the other end of the polygon. So let me start from O. Then I will draw parallel line parallel to link 3, because we know that F34 is parallel to link 3. So I am going to draw from there. I am going to draw a parallel line. That's it. We got that. It intersects here. Now we know the direction of the force. The coupled polygon must be closed, and hence if it acts here, this must be upward and this must be this direction. That's it. Yes, we got force polygon. Shall we to find the unknowns? Yes. Now we'll come to the calculations part. This length AB gives us F14. This length gives us F34. F14 is equal to measure vector AB multiplied by the chosen scale. So for me, it comes around 1.7850 Newton. Similarly, I could find the other force F34 by measuring vector OB multiplied by scale 3200 Newton. From link 3, you can write F43 will be equal to F23, which will be equal to this F34. So we have got the answer. So now we can go to link 2. So link 2, now I can write, we have got these two forces. To find torque T, it is a couple, right? So I know the force. If I know the perpendicular distance between these two forces, say I call it as a H. If I can measure the H, I can find the torque easily. So I can extend this. Now I need to find, okay, this is what I need to find H. So finally, we have to find torque T is equal to either F32 or F12 multiplied by H, which is nothing but 3200 multiplied by H. I need to measure the H now. It comes around 2 centimeter for me. So 2 multiplied by scale. So this comes around 100 mm for me. So I will get 0.1. So the answer will be 320 Newton meter. Can we able to identify the direction? When these two couple acts, the couple will be acting this direction. I mean, that we call it as counterclockwise direction. Yes, shall we summarize all the results that we have obtained? So that's it. This is the graphical method that we have used to do static force analysis of slider crank mechanism. Hope this video helps you and you understand the concept much better. So that's it. Let me see you in my next video soon. Take care. Bye.